Okay, on to question 3. I think I've just moved my page. Let me try and undo that before. There we go. On to question 3. This graph shows how a skydiver, how their vertical velocity changes with time during part of their descent. So we've got initially accelerating, getting faster, and then sort of leveling out at about 50 meters per second. The skydiver is very close to her terminal velocity after 20 seconds. Explain, making reference to air molecules, how this velocity arises. So terminal velocity, the general idea here is the faster you go, the larger the drag force, and therefore as you accelerate downwards with a constant downward force, your weight being constant, the upward drag force increases until those two forces are balanced, and then you'll travel at a constant velocity. It does say making reference to air molecules here. So that sort of suggests to me that we're going to have to make some statement that describes how that drag force comes about. So, collision with air molecules when moving. I've not spelled molecules correctly. Let's try that again. Collision with air molecules when moving causes transfer of momentum, I'm going to say. And hence drag force. I'm going to make some sort of reference to the idea that the faster I move, the larger the drag force. And possibly even some reference to y. So drag force increases with speed, since at higher speed we collide with more air molecules per second, and a greater momentum transfer with each collision as well. This is a 3-mark question, and I'm probably going to write more than is necessary, to be honest. So I've explained why the drag force increases with speed. So downward force is constant. That is simply the weight. But upward drag increases with speed. Once those two forces are balanced, no further acceleration happens. So I feel like that's a pretty comprehensive answer, and I'd be reasonably confident of getting 3 marks for that. The mass of the skydiver is 68 kilograms. Use the graph to determine the vertical force of air resistance after 7 seconds. So what we need to think about here is resultant force is mass times acceleration. Therefore, the resultant force on this skydiver, mg minus the drag force, equals mass times acceleration. So the air resistance force, the drag force, must therefore be equal to mg minus ma equals mg minus a. So let's have a look at the graph and see if we can find acceleration from it. After 7 seconds, so let's have a look at our scale, 6, 7. So that is at this point. So what we're going to have to do is, to get the acceleration at that point, we're going to need a gradient for this graph. So I'm just going to draw on a tangent. Excuse me, sorry. At that point, I'd like that to be a little steeper, I think. So this is, oh no, here is the 7-second mark, I think. I would imagine the mark scheme is going to allow a little bit of leeway in terms of the gradient that you draw. Rid of the ruler. But look how neatly this intersects at these 2 points. So let's find a gradient there. So delta V here is equal to 20. Delta T is equal to 10. So going back to the actual question, acceleration then, delta V over delta T equals 20 over 10. It's 2 meters per second squared. Therefore, oops, that's not an F. The drag force is equal to the mass, 68 kilograms, multiplied by 9.81 minus 2. And that's a job for the calculator. Giving me 531 newtons. Okay. Little bit of exam technique. In general, when you're finding a gradient or finding something from a graph, I would strongly recommend writing onto the graph what you've actually done. So drawing construction lines like that for finding a gradient is generally very good practice because it makes it explicitly clear to the examiner where your numbers have come from. It is easy to lose marks. It's easy to lose marks by simply not making it clear how you've used the graph. And obviously you could write words to suggest that we've found a tangent at that point or whatever. But I think it's generally quicker and easier to simply have a clear diagram on the actual graph itself to show what you've done. Part C. NASA, funded by the American government, has developed parachutes that will safely land spacecraft on other planets. Has also been involved in the development of parachutes that can safely return a light aircraft to Earth in the event of a fault in flight. Discuss whether you believe this to be an ethical use of the money. So, these types of ethical discussion questions, there's 2 marks here. So I would suggest, in general, when I see discuss, I think I'm aiming to make a point for and a point against. This is about the use of money, and we're being asked about whether it's an ethical use of money. So points to make here: it could potentially save lives. when it's applied to aircraft on Earth. The Earth should have a capital E there, but anyway. So that's a 0.4. It could save lives, which is obviously a good thing. The counter argument to that is that money spent researching landing on other planets is a lot of money typically. Landing on other planets costs a lot. And arguably that large sum of money could save even more lives if used for example, mosquito nets or something like that. If used for medicine, for example, or clean water in third world countries. Okay, question 3 done.